not presentation. All right, so we switched to English because we have foreign guests today, at least. So, okay, and hopefully also there are young students, young researchers coming from abroad and who may not be acquainted yet with our language. So now we will move to English. If you allow me, I will also try to be a little bit more at ease myself and distress a little bit. So I take away the tie. It's really not my habit too. I have one. And all right. So the goal of these days, it's really to introduce to you, to the entire community, this project, because this project was put together by a number of people, as large as possible, always a little bit in a rush, when there are deadlines and so on. So part of the community may have been not really aware of what was going on and may feel to be a little bit excluded on the side. This is not the case. And really the goal of these days are not really talk about new scientific results, so this will be the object of future meeting we will organize, but really explain to everybody how this project will work so that everybody has a chance to come on board. All right. So this is the introductory talk, and then throughout these 3 days you will have more and more details. So this is a general presentation. So first of all, for those who don't know, maybe our foreign guests, we speak about this PEPR, what are they? So PEPR is the acronym for, in French, Programme Équipement Prioritaire de Recherche, which we can translate as Priority Research and Equipment Projects. They are funded in the frame of the Recovery Plan, France 2030, and the Recovery Plan devoted 3 billion euros for actions of fundamental research. And these are divided into groups. So the main group, which gets 2 billion in total, is our PPRs, which are concentrated on questions of national strategic interest. So they are organized in a sort of top-down fashion. The government indicates what should be investigated. The researchers come together to do it, like cybersecurity, artificial intelligence, decarbonization of the economy, new medicine, and so on. But a billion, it's not negligible, has been devoted for exploratory projects, and these are bottom-up, so there were no indications from the government, and it was really to the researchers to come together and propose something, as we did. And 20 projects, so for about 50 million each, have been selected or will be selected by an international committee. And for those which have been selected so far, I have to say that most of them concern science which is quite applied one, so the interest, the utility for the society, for the economy is straightforward. These are PPRs devoted to material science, to ecology, to managing of risks, climate change, and so on. Up to now, our project is quite atypical because the subject, origin of planets and life, is really one of fundamental science, and you don't see straightforward any application. My father, who was an industrial chemist, when he knew that I wanted to be an astronomer, used to tell me, astronomy is a science with which or without which it's the same. And so it was quite of a surprise to be selected in this framework because the money essentially comes from the recovery plan. So as I said before, the questions of origin, planets, life, is there life elsewhere, are as old as humanity. So you may wonder why we should do something special today. And we should do something special today because it's really a special time. As I hinted before, recently the framework changed completely. In particular, in the last 2 decades, we've found thousands of planets, and many of them are in multi-planet systems. And we found in particular a category of planets called super-Earths, and these super-Earths are super interesting, and because they look like the Earth in terms of general composition, although they are typically bigger, and some of them, most of them are very close to the central star. We have a good understanding now about prebiotic chemistry, and in terms of solar system formation, we have now a quite clear chronology of the events, thanks to the constraints given by cosmochemistry, and thanks to space missions in particular, we have now a good understanding of the inventory of the properties, chemical and isotopic properties of the bodies. But in the future, and we hope not too far away, just a few decades beyond, we should still do a big leap forward, and we hope to detect real Earth analogs, not only in terms of mass, but also in terms of distance from the central star and around the solar-type stars, which are more quiet than these M stars around which we discovered the so-called habitable super-Earth so far. We hope we will understand this transition towards life, which starts with the auto-organization and replication, and this seems to be a very low probability event, so it's hard to study in the lab. You need to parallelize your experiments. This is the goal of multifluidic techniques, and the role of the environment seems to be a crucial one in order to drive this random evolution towards auto-organization and replication. We will hear more about that. I'm not really an expert of biology, of course. And then for the solar system, we will refine the history of its formation, and in particular the history of materials, of matter, from stellar synthesis down to the constitution of the planet. So our PEPR is based on, as I said before, on 5 research axes, which are sort of excellence in our country, and which are this one. So one is clearly about the detection and characterization of extrasolar planets, and we think direct imaging is the future. Now, today, we characterize the atmospheres of the planets using transit spectroscopy. That's what James Webb is doing. That's what Ariel will be doing. But in the future, if we want to characterize Earth analogs, they are unlikely to transit. So direct imaging is the way. And the second axis is cosmochemistry. So the analysis, chemical, isotopical, of the primitive matter of early Earth and also extraterrestrial bodies through the study of meteorites, but also now all space agencies, NASA, ESA, JAXA, Chinese space agencies, more and more devote their activities to go collect samples in space, bring them back to Earth, and analyze them, these samples, without any contamination from Earth. And we are also, our community is on the forefront of this activity. The third axis is based on the knowledge of Earth science here in France, and essentially it's studying the Earth in its globality, not just details, one mountain change, one ocean ridge, but really the Earth in its globality, and understand what makes the Earth habitable. Of course, the distance from the sun, but not only, and in particular we think that the internal geodynamics, which may be an oddity of our planet or specificity of our planet, plays an important role to make Earth habitable. The fourth axis concerns the emergence of life. This is basically lab experiments and bioanalysis of samples of early Earth or early Mars. So samples from Mars should come at the beginning of 2030s. And the fifth axis concerns numerical simulation, data analysis, and the control of instruments. So it's all goes through intense use of computer, and you know, computers now undergo a revolution. There is a transition from CPU to GPU based, which allows to make calculations of a complexity that was not possible to do before. And of course, artificial intelligence gives a great opportunity to analyze images and also drive instruments on real time on such frequencies where the humans cannot do much. So we want to take advantage of this numerical revolution in order to be more powerful in all our activities. But as I said before, we think that in all these domains, what we really need are technological steps forward. So for instance, if you want, of course, to image an Earth and characterize its atmosphere, you cannot do it today with the instruments today. So you need a new instrumentation with much higher contrast and resolution, so that we need to develop. So we have selected 4 work packages that aim to develop the required instrumentation with the goal to be prepared, to prepare the French community to take a leadership when the time will come to construct the last instrument for the ELT PCS. For cosmochemistry, so at the end of this decade, on the beginning of the 2030, we will get new extraterrestrial samples from the moon of Mars, and in particular from Mars itself, the famous Mars Sample Return mission. And of course, we need to be prepared. And to be prepared, we need new instruments to analyze this material better and better with higher resolution, higher precision. The analysis of these samples, some are guaranteed to France, like the samples of Phobos. The samples of Mars are not guaranteed to anybody. The scientists will have to submit proposals for the analysis of these samples. And of course, if we develop instruments that allow us to do better than the others, it will be easier to win this competition. In particular, one instrument which will be developed by CNES will be the contribution of France to the quarantine facility for the Mars sample return, because they will allow the analysis of the samples in a strict bioconfinement, because when samples come back from Mars, they might be contaminated, probably not, but we need to be safe. And so for the first months or years, these samples have to be screened in a secure bioconfinement. Axis 3, so geophysics. So far we have only one project, and this is devoted to extending, to developing an instrument that is a robot, actually, that's capable to deploy seismometers at the bottom of the ocean floor. That's because we want to understand the internal geodynamics better, and this is done using seismic tomography. But so far, seismic tomography is limited in resolution by the fact that the only seismographers are on islands or continents, and 3/4 of the Earth is covered by water. So by being able to deploy seismometers, like we have been able to deploy seismometer at the bottom of the oceans, like we've been able to deploy a seismometer at the surface of Mars, we can really increase the resolution of mantle tomography and understand better the internal geodynamics and its relationship, for instance, with plate tectonics and climate regulation. On this fourth axis, also we need new generation of instruments to enhance our capability of doing lab experimentation. So we have selected 3 projects. One is about microfluid techniques. It's a sort of parallelization of lab experiments in droplets. And we want to be able to enhance by at least an order of magnitude the capability of this instrumentation. And on the 5th axis, as I said, we want to really exploit exascale computing, but this requires to rewrite codes and also use artificial intelligence for image analysis and to drive instrumentation on real time. So you can see here all the arrows. Now, I don't go any further than that, because during these days, the responsibles of each of these axes will present these axes, and then the responsible of each of these work packages will present their goals and their projects, and so you can then talk to the people involved if you are willing to contribute. Because, as I said, these instruments or software that we want to develop are designed to help our science, but are also designed to have a number of applications to other more applicative sciences or even the industry. We got, at the time we wrote the proposal, the support of many companies that really witness in their letters that they are interested in what we develop, to use these instruments themselves or to commercialize these instruments in the future after they will be patented. Of course, a PPR cannot fund industry. It's fundamental research, so industry does not get a euro out of all of this. But we hope, and this is the goal of the recovery plan, that the technology and the prototypes that we will develop will have interest for the industry, and then the industry will take advantage of them later. All of what I explained is, so this part here that now is shrinked, is part of a global environment. And first of all, I would like to mention the 6th axis, which I put a little bit aside because it's not science, hard science as we call it, but it's rather human and social sciences. This is important. It has links with all the questions that we address in the other axes. And in particular, we will have a presentation of this tomorrow at 11:30, and there are a number of questions that our colleagues will approach, so study how different cultures represent life and interpret the possibility of lives elsewhere. It will be following the researchers in their activity in order to analyze the scientific process in understanding the origin of life, and they will also develop new techniques for the communication with the public, because it's very delicate. It's unlikely that all of a sudden anybody can announce we have discovered life. There will be first hints that life may be on some planets and so on. So it will not be, at least in the first time, a certain discovery. So you have to educate the public of probabilities, and the public has to get excited, but has also to understand that then there are negative results. So this is part of the game, and it's very difficult. For instance, I have experience in the past with research on near-Earth asteroids that sometimes are discovered on trajectories that can collide with the Earth potentially. And then, so the great announcements on newspapers, public panics, and then 1 week later, the orbit is refined, is not crossing the path of the Earth anymore. So say, okay, there are no risks, people are confused, and so on. So it's really, we need new techniques of discussion or presentation with the public in order to educate the public in understanding the difficulties of research, and the fact that research often does not provide certain results, but give results with a certain probability. And also the international law space, something which are very fuzzy, and they will be investigated, and maybe some proposals for better law will be developed. So enough for that. We will hear a much better presentation tomorrow at 11:30. We will have a call for new instrumental projects in 2025, because we selected 17, but we don't have the crystal ball. So these are the instruments that have been proposed to us, to our committee, but we may have missed some. Somebody may have missed the opportunity. And also, with the development of things, new ideas can come out. So we have reserved a budget that is capable of support 4 new projects. And these will be selected, as I say, in 2025, again by an international committee. We will present how this new call for projects will be made, and also tomorrow at 5:15. We have a program for the scientific follow-up of the PEPR, because, as I said, the PEPR is mainly focused on instrumentation, so that we not really support research with the existing instruments. But there is this program which is supported by CNRS, by INSU, by CNES, by ourselves, with some envelope. And here, the community, will be able to submit research proposals, so not related to development of new instruments. There is a call open, because the community is not so aware. We obtained from CNRS that the deadline is delayed compared to the usual deadline of INSU to mid-October. So if you understand what it is now, you still have 1 month in order to submit your proposal. And so this will be very important, and this will be presented in 2 days, on Wednesday at 9 a.m. And then we have these actions of communication towards the public and formation of students that the minister alluded to, and they will be presented also on Wednesday at 9:30. So this started already. We issued a call for ideas, for actions, and we selected some, we funded some. They will be presented on Wednesday, but we have not finished the money devoted to that part, so it's an open tap, right? Now it's au fil de l'eau. Everybody who has an idea can propose the idea, and from time to time, the coordination committee will analyze these proposals. So a lot of opportunities, even if you did not take part to the original writing of the PEPR proposal. So in terms of money, so we got 45.5 million, and for 7 years. And as I said, most of the PEPR is devoted to instrument development. The 17 projects already selected get 35.9 million. There is a 4.8 million still to be attributed in 2025 with the new call for projects. And so this, 35.9 plus 4.8 is 40 something. So it's most of the money, 90% of the money. But we have an envelope of 4.8 million which are devoted to actions for formation, outreach, organizing meetings like this, and so forth. It's so far the PEPR really federates the national community. Here you can see in colors the various projects in each axis and the different labs in different cities that link together. The PEPR includes a large number of institutions. Of course, CNRS is the leader, but there are many other institutions that participate with in this project. And of course, we don't start from scratch. Our work was facilitated by the fact that before, a number of university sites decided to develop actions, local actions at the level of the university on origins. And of course, this experience started before and was a great help in putting this proposal together. So now the question is, how can we articulate the activity of PEPR, which is a national one, with the activities at the local university sites? And so on Wednesday, we will have the presentations of the most relevant of these projects. And then we will have all a round table in order to discuss about these relationships, as well the relationships with the national programs of INSU and the other opportunities for funding. So in terms of governance, I think it's important that you know this so that you can know whom to address to. If you have questions, you want to participate, I have the honor to be one of the co-directors, but each axis have two people responsible of the axis that you see here, and Maud Langlois is a co-director of the general project. So these people are in contact with those who are responsible of the working package that exists or will be funded in the future, and the communication is done that way. In addition, there are a number of people who are invited in this executive committee. So Peric Pitrou is responsible of the human and social sciences activity, and then of course Martin Giard and Guy Perrin and Marie-Christine Angonin as people who follow us from CNRS, the ministry, and ANR. And on top of that, there is a strategic institutional committee. This is made by the representatives of the main universities or institutions that support or participate to the PEPR. There are many more than these, so we had to do some grouping, shotgun marriages, and here is the list of the people who sit on the strategic committee, institutional committee. Basically, this committee follows what we are doing. We report to them once per year and tell us what to do or their opinion on that. There will be also an international scientific committee, so this will be made by international experts, and they will have an advisory role to follow what we do and give suggestions to improve if we don't do well enough. So what's going on now in this meeting? So today we have several people that we invited from abroad. They are responsible or co-responsible of analog projects, but as you will see, different projects have different flavors. So they will give their presentations. We have 5 today. And then this will be the occasion also to discuss how we may potentially collaborate with each other. And then for the rest of the day and tomorrow, we will have a presentation for each research axis and for each of the work packages so that everybody can really understand what we are going to do. Then we will present all the other actions of the PEPR, so the new call for projects, for instrumental projects in 2025, these actions on public outreach and teaching that we have selected, and the opportunities to select the new ones, and the famous program of for scientific follow-up that is currently open and for which we hope to receive many applications. Then on Wednesday, we will the responsibles of the different initiatives on origins in various university sites like Grenoble, Bordeaux, Marseille, and so on, will present what they are doing, and then all together we will discuss in a round table open to the questions from the audience, of course, about the national coordination of all these different activities. The important is not to disperse and not to be redundant, but to really work together so that we are as effective as possible. And Wednesday we will conclude with, I hope, a nice and friendly discussion. So thank you very much. And I open to some questions because I think we are ahead of time. And otherwise we move forward. Thank you. Are there any questions on this general introduction? Okay, if not, then we pass to the presentations of the foreign initiatives. I believe, so this is for tomorrow. It's not the same presentation. So I believe the first to speak is Inge Loes on the Dutch initiative. Is that right? Is Inge here? She had a train this morning from Amsterdam. If Inge is not... who was second in the list? Barbara Ercolano. Barbara, did you arrive from Munich? Okay, great. I did not see you. Thank you, Barbara. So, Barbara Ercolano will speak about the Bavarian initiative of origin. She's coming from Munich. Thank you.
Can I use a space changer?
So thank you Alessandro, for this very nice invitation today to present our Origins initiative in Munich. I also just made it in time because we actually were on a dead plane for about 45 minutes and had to change plane this morning, so waking up at 4 didn't really help. Universe was the first excellence cluster that was set in Munich. And we are now already in the second round of the Origins initiative, which is basically a nationwide initiative from the German Science Foundation to fund mainly universities for interactive work on topics of different science topics. So at the LMU, and particularly in Munich, we have been very happy to have been able to have these excellence cluster initiatives already for over 10 years. In fact, I am the daughter of such an initiative, if you can say so, as I came with the first Universe initiative in Munich. Universe wanted to understand the origins of the universe, and we made quite a lot of progress in different areas. And for the last 4 years, we had a new cluster called Origins. Now, Origins basically is based on the successes that we had in the Universe cluster, which was a very broad cluster, including both of the two Munich universities, the LMU, where I'm in, so the Ludwig Maximilian Universities, and the Technical University, but also all the other institutes, research institutes that are in Munich. So the Max Planck Institute, ESO, and the LAZ, which is basically a large computing center serving the whole of Bavaria. Now, what is the idea of origins is broader than just looking at the origins of life. Origins actually searches for the origins of the visible structures in the universe, all the way from the first particles to the first building blocks of life. And in the first phase, so the excellence clusters in Germany have generally 2 7-year funding phases. So it's very similar in terms of funding of what I heard from Alessandro. And we are already coming to basically the 5th year of the first funding phase, which was led by Andy Burkett at the LMU and Stefan Paul and ITU. And we're now really working hard to make a proposal for a renewal cluster for a phase 2 origins, for which I will be speaker together with Stefan Schönert of the Technical University. And so, what is universe and origins about? Well, the idea is that in Munich, we have a very, very, very unique setup of lots of different expertises, lots of different institutes. And so we kept the origins cluster very broad. So it includes basically a synergy between particle physicists, astrophysicists, biophysicists, and now we plan for origins 2 also to include geoscientists, to basically look at some very broad but also very fundamental questions, which are basically listed here, which are what are the fundamental forces and structures in the universe, how did our universe form and evolve, how the constituents of the universe form from the cosmic web. So we're talking about stars and planets as well as galaxies, of course, and how basically the building blocks of the universe came to be from simple atom and prebiotic molecules. So the search for life on the Earth is not concentrated just on looking how the prebiotic chemistry could occur on Earth. There are also experiments on that, but it's trying to take a broader view to see, basically answering the question of is life in the universe quasi a constant? We haven't found it yet, but is basically the universe teeming with life? And of course, you know, while we're not planning specific instrumentation to do this, but we're trying to basically make the links between all these different subjects to try and understand this question on a broader sense. And for that, the origins cluster is based in basically 5 main research areas, which, as I say, span from particle physics, cosmology, astrophysics, biophysics, and geophysics. But also we have set up what we call the interconnected universe. And this is a set of projects which are highly interdisciplinary, which are called connectors, which basically make sure that people from different institutions, but also from different research areas, come together to then look at more specific questions. Because up to now, you've seen that the scope of origins is very, very broad. And so we want to retain some deepness in this broadness by having some focus areas that really make use of the different expertises that we have in Munich. And so these are our connectors, and the connectors are basically 9 different large projects on specific topics which I will talk about. So what the origin scientists enjoy, as well as the opportunity of working together, but also a support of infrastructures that basically join us together. So we have the MIAP Institute, which is a conference center which hosts 4-week-long conferences. This is a think tank inviting different scientists from basically all over the world to hold conferences at the cluster with 50% cluster member participation. We have a data science lab, a computing center that is dedicated to origin science, and also a ice and dust sequencing lab. So just to look on very broad lines on the science that is done in Origins in the different research areas, we start basically with the fundamental forces and particles. And the idea of this research area is to understand how the universe is governed by these fundamental particles and by their interaction, and also understand what determines basically their dynamics. And so we based a proposal on questions. This is why my presentation here is also telling you what the questions are that we're trying to tackle. And so one of them is, what are the principles of quantum gravity? How do you constrain the quantum fields theory in phenomenology and cosmology? What can be said about the known particles, like, for example, the Higgs boson? This was a big thing, of course, when we were writing the proposal. It's not anymore, almost. But are there new particles? Is there a search for new particles? How are the properties of the strongly interacting matters at low energy? So this is a huge spectrum of topics just in this research area, which goes basically from low energy particle physics to high energy particle physics. So even though this sounds like all like particle physics to a non-particle physicist like myself, this is already bringing together people that otherwise wouldn't have been working together from the two universities and the Max Planck's. We also have a research area on astroparticle physics, which is basically looking at elementary particles and what is their role basically in shaping the universe and also causing some of the most spectacular astrophysics phenomena. So, and the questions here are about the nature of dark matter, the role and the mass of the neutrino, the origin of the matter and antimatter asymmetry, and the source of the cosmic rays. For that, we're also synergetic with several different projects funded by the EU, which also funds laboratory experiments and detectors. Then we go on to cosmology. The classical cosmology is also not really here. This here also joins people from observational theoretical cosmology, large-scale structures, looking at basically and how these cosmic structures like the galaxies, but all the way down to stars and planets, originated basically by the first quantum fluctuations in the early universe. So here, the main questions are about the origins of the initial density fluctuations, what are the astrophysical probes of dark matter, the origins of cosmic acceleration, and what is the role of the massive neutrinos in cosmology. Again, for a non-cosmologist, this is cosmology, but when these people talk to each other, they also need to do quite a lot of effort to try and to make the talks understandable to each other. So this has been a great achievement, I think, of the Excellence Initiative being so broad that has allowed us to learn to speak a more common language and try to make our science more digestible also to non-experts. And this is exactly what is needed to be able to take advantage of what has been learned in a different field and apply it to your own field. So we come to basically what involves the whole of astrophysics, which is basically going from the large scale structure to galaxies, stars, and planets. And here we have some of the star formation and planet formation projects, but the idea here is to basically stop thinking of these entities as closed systems. So the focus in this research area is not to do star and planet formation. People do it in Munich on their own, with their own funding. Here is really to start thinking outside a protoplanetary disk, think outside a star, but basically link it to the environment and link it to the multi-scale environment from which the structures are coming from. So the deal here is to try to understand the multi-scale and also the multi-scale in time of these structures. So if you think of a disk, if you think of a star, you basically have to start thinking of the environment which formed in and take advantage maybe of the large-scale simulations that have been done and focusing on those. This is just an example of what we try to do here. The final research area can be described as biophysics, but again, this is a collaborative effort between biophysicists, chemists, molecular biophysicists, and also astrophysicists to try and understand the emergence of life from what they call dead matter. And understanding it in the lab will also tell you how easy it is for it to form somewhere else in the universe. So this is basically the overarching goal, of course. And there are a set of questions here, which are the origins of complex organic molecules in the interstellar clouds. So what is the inventory there? What are the building blocks that we have? How can we go about discovering more? Which non-equilibrium metabolism supports the origin of life? What is the origin of prebiotic molecules in planet-forming regions? Now, how the information control, and particularly replication, ligation, form from these simple building blocks. There's a lot of lab work that's going into this research area, and let's say the job of the astrophysicists there and also the geophysicists is to try and to give some boundary condition to this lab work. So what could have been the possible conditions? What are the obvious parameter space that we have to investigate? So finally, how were the molecules confined over extended periods to foster the origin of life? This is also a very interesting question about the containers. There weren't really containers. Maybe at the start, what could have been what sort of molecules, or maybe what sort of structures could have been the containers for the early life? So these are our research areas, which we envisage keeping similar in Origins too. And now I give you an idea of some of the interdisciplinarity that can come out of this. So this is, for example, a recent Nature Review paper which was led by the group of Dieter Braun to try and understand the physical non-equilibria for prebiotic nucleic and chemistry. But this was done in collaboration also with my group, and collaboration with geophysicists, and also collaboration with theoretical biophysicists to really try and understand how this could have happened maybe, or how could this be happening in other possible astrophysical environments. So we sat a lot, we talked a lot, but this is exactly what the cluster is trying to do, is trying to start this conversation across the different fields. So now, what's new in Origins 2? As I say, we want to keep the research areas with their focuses. Of course, the questions will be updated to what the current challenges are. But we realized that within the next 10 years, of course, there will be a lot of emphasis and there will be a lot of information coming from the observations of planetary atmospheres. Of course, as Alessandro said, not really terrestrial planets yet, but this is what is the aim for in the next few decades. And one thing that is very clear that many groups are gearing up for is the fact that we need to understand biosignatures. And biosignatures, of course, as Alessandro said, are very difficult to understand. So in the sense that if you say, I have found life, actually you have found a molecule. And your job will be to prove that what you have found can only be made by a living system. And here, in order to do that, you need to have a template of a non-living system. And this is where geophysics, particularly volcanism, also gives you a lot of information to try and understand how does an atmosphere without life evolve. And so this is something that we want to do in Origins 2, also taking advantage of the geoscience chair at the LMU, led by Don Dingwall and Yann Lavallée, who are setting up very interesting experiments trying to understand the evolution of abiotic atmospheres in this way. So this is something that is new, and of course we also have new chair of planetary atmospheres with Kevin Heng, who will look more on developing Bayesian interference methods to basically do atmospheric retrievals. Also, we want to use our expertise in science to try and understand what were the chemistry that was possible in this early Hadean period of life. So there are very different, let's say, spaces that were empty in Origins 1 that need to be filled by geoscience in order basically to go to the next step. So we focus on geophysics, astrophysics, and biophysics, particularly in a new connector. The connectors will completely be updated in Origins 2. This was the idea of having this interconnected universe system, which would be a fluid structure. So this is obviously if you have 60 millions or if you have 45 millions and you assign them all to the last penny for a project that is 7 to 10 years in making, then it's difficult to really react quickly to new challenges and new science that becomes basically at the forefront that you couldn't have foreseen. And this is what our connectors are. So these are basically fluid funding that we can assign on structures that basically change. And for the Origins 2, we want to have, again, connectors on astrochemistry, biophysics, and geoscience. So here are some examples that I have shown. So we have a connector on dust, for example. This is a very, a connector on dust in the universe obviously brings together many different communities because dust is very important from planet formation, but also for cosmology, and also brings together different techniques and the development of different techniques how to treat dust in different types of environments. So this is just an example of how these connectors would work. So we also have this connector on exoplanetary habitats for molecular life, which brings the geoscience in. On chemical evolution, we have connectors on particle physics and astrophysics, looking at antimatter, cosmic accelerators, matter under extreme conditions, so these are basically neutron stars. And we have connectors, again, joining particle physics, cosmology, and biophysics. An interesting one that we didn't have is the emergence of structures, complexity, and information, which we started basically playing with in Origins 1. But this is basically looking at fundamental principles that drive pattern formation and self-assembly, which turn out to be actually quite similar, both for biomolecular and astrophysical systems. So this is really an idea at the moment. There's been MIAP meetings on that, and we hope to basically make this more concrete in the second phase. So a few words about MIAP. MIAP also has quite a lot of funding from the cluster, so it's completely funded from the cluster at the moment, and has become an established think tank for and guest research center. So everybody is invited to present MIAP conferences, which are basically 4 weeks with minimal amount of talks, just one talk per day, and the rest of the day basically really dedicated for the scientists to interact with each other and start new collaborations. We also have seed money, innovation funds. Again, this allows us some flexibility in how we assign the funds as we go along. So if a new idea comes in, a new challenge comes in, a new observation comes in, you're stuck with all your 60 millions doing something else that maybe is not that interesting anymore. So we basically keep something behind for this innovation fund. So people can apply throughout the Origins time for new projects, new PhD students, also new hardware if it's needed for the Wendelstein, for example, or also for new detectors. This is something that has been very useful, and we want to improve it in Origins 2. We're also very engaged with schools and trying to basically make some of these origins concepts, particularly those more difficult to understand for the students, a little bit more, let's say, approachable. And we have basically a W2 professorship, which is on science communication, which was assigned through the cluster, and now we want to develop this Origins goes to school or to schools for the second phase, which really brings the Origin science into curriculum for the schools, including some VR and app, and there's a lots of ideas that are being developed. We have Of course, lots of PhD students which do great work, and we have these PhD awards, which also have become quite well recognized for the students that get them, tend to get good offers and can put them on their CVs. I'll come back to the gender balance in a minute. That's not very good news, but we are trying to improve on this by having a dedicated fellowship opened just for female scientists. This is the Vera Rubin Fellows, which we already had 3 rounds of 3-year positions. We also have a standard fellowship, the Origins Fellowship, and again, this is having a lot of resonance. It's also a lot of work. We have hundreds of applications for every round. And now I'd like to say just a few words about the structural organization of Origins. What we have is basically all the decisions in Origins are democratically made by a voting system by the Origins Research Board. So the Origins Research Board are members from both the research units coordinator, the interconnected universe, also MIAP and all the infrastructures. And also we have PhD and postdoc representatives, and all have equal voting rights. So what the speakers do, they only propose things to the research board, and these then are put to the vote. And we are advised by external scientists, a scientific advisory committee that comes every year, attends our science week, which is once a year, and also informs the council, which includes several vice presidents from the different universities and also the cooperating partners. So we think that in that way we have a, let's say, a trouble control system which informs us early if something is not functioning or how we can improve basically on a yearly basis. We're a pretty large cluster. We have 120 PIs. So 80 for them received funding in 2022. Those who didn't receive funding are still PIs because they can then apply to basically these innovation funds, the seeds money, the visitor grants, so they can still receive funding from the cluster, but they don't have an assigned PhD or postdoc or hardware center, for example. This is what this means. The same for the postdocs. We have 120 postdocs that do cluster-related science and participate to all the cluster lives and the activities, and 50% are paid by the cluster, and the same for the PhD students, about 180. So it's a very large and a very diverse community that requires a lot of effort to basically keep effectively talking to each other. And so this is why we have all of these different infrastructures and all of these different activities, so that people at least know each other and can work with each other more efficiently. So this is basically the breakdown of PhD and postdoc students that are funded by the cluster. So DFG funds mainly universities in Germany, so most of the money is going to the LMU and the technical university, but of course our partners also have their share, and it's very important to have this kind of shared PhD and postdocs to bring basically the Max Plancks and the university working more closely together. Here we come to the gender statistics, which, as I said, this is something that we definitely need to improve on, and we're doing our best to improve on. At the moment, we're definitely not doing good. So we have 78% males and 22% females. It doesn't matter which way you try to turn the statistics. If you just look at the PIs, if you look at the PhDs, it's always the same. This, in some way, is some good news in the sense that you don't see that there's lots of female PhD students and only one in a leading position. So it's really reflecting a problem in the community. Don't forget that we have a lot of particle physicists in our community. So the research area A and the B are particularly extremely male-dominated, and this is a problem in the whole of the particle physics community, of course. And there is a lot of efforts that are being made at CERN with different politics, but it will take time. We, in our, let's say, confined and limited influence that we have on this general problem, we're getting active with basically an Origins mentoring for women to at least ensure that that the women, the female researchers that we have also do continue and do well in their career to then achieve leading positions. And so we have a mentoring system. We want to improve now this in Origins 2. At the moment, all the people who are doing this work of mentoring and equal opportunities are all female. And so we thought that it's time that our male colleagues also help us in this. So we will have a mixed gender equal opportunity and mentoring system for female students and postdocs who want to have it. We have interview trainings, personal career service. So we have a set of also activities. So self-management course, etc., a writing course that we have we've been able to offer. But for Origins 2, we definitely need to do more. So we have already started speaking also to HR and to the way that basically the hiring are being made, and there are some more radical policies that are being planned now for the second phase to improve on this shameful 22%. So thank you for your attention. I thought I hope I could give you a flavor of what the Munich initiative is, and this is what we call our spiral of complexity, in which basically we want to really go from the initial particles and forces all the way to replicating DNA. So thank you very much.
So there are questions for Barbara?
Thank you, that's great. I mean, I'm aware of this Origin program since 2017. I think this is where you started, right?
Yeah.
Could you explain a bit the funding structure in Germany? I'm a bit confused here, because this is from the Excellence Program 25, going to 25, right? The Origins 2 is going to the next round after 25 to 32, or, I mean, it's fully funded right now, and you are going to until 32? What's the time scale
right.
talking
That's
about?
right.
Could you explain a bit what the
That's
situation?
Right, that's it. So we had 2 rounds of Universe. That was the previous cluster that ended basically in 17. And now we have the first round of Origins 1. So each cluster can be funded for 2 rounds, and each round is 7 years. So we are on the 5th year of the first funding phase of Origins, which is the second cluster. So Universe had Universe 1, Universe 2. Now we are on Origins 1, almost at the end. And then there will be, hopefully, if we're successful, Origins 2 starting at the end of 2025. No, we are applying, we are planning for it. So we have Origins 1. So all that I showed you is from Origins 1, which will run until 2025. And each excellence cluster can have 2 funding regions. So if we're successful, they start after 25. Yeah, I will emigrate to Mexico if it's not successful.
D'autres questions? Not, I have one. So your program is much broader what we have here, as I explained before, because you touch cosmology, fundamental physics, and so on. So if you restrict to activities closer to ours, so planetary science, geophysics, exobiology, what is the volume of the support that you have, order of magnitude, more or less?
Yeah, so I did have a slide I didn't show you with a different breakdown, but so let's say 60 million was the original for the whole cluster. Then there was a cut to 45 to all the clusters across Germany. So for the first funding phase, we had 45, and it's roughly divided by 5 into in each research area.
About
so
9-10 for the
1/10, yeah. But you can put, if you put together astronomy, then you have 2/5. Yeah, so you have 2/5 of this going into what you can call really origins-related science. Yeah. We hope for 60 in Origins 2 because the minister has increased the budget again. So.
And do you have some instrumental development in the sense that we aim for?
No. We don't have it. We have where we can pay to join missions. We can support missions. but we don't have any specific instrumental development for this.
Okay. Steve?
Good morning.
Hi.
We've heard this morning about these excellent Origins programs. These are training programs. We're training and recruiting many new people. You pointed out the gender imbalance, especially in this program. So what, besides the training, will be offered in terms of actual positions for all of these people that we're training? I'm not hearing so much about that and what funding lines will be devoted to create positions for these talented people. Thank you.
This is a very good question. So at the moment, so for the first Origins part, we did have a very limited amount of W2 positions that were formed for Origins, but these have to be open to the community. So they were not for young people recruited by Origins who could stay, let's say, at the LMU. So they were open positions. For Origins 2, we won't even have those because we already done the recruiting for the permanent position in the first phase. What we can offer is just a training. So we don't have any permanent positions that are associated. These are something that is done by the ministry. It's not done by the DFG. So, yeah, the DFG does not have any influence over what the universities do.
You presented the fundings for PhDs and postdocs. Why did you make the choice to co-fund these PhDs and postdocs rather than funding them fully on your budget?
Oh, no, sorry. This, I misspoke then. This is not the way that it's done. So we have 120 PhDs, let's say. 60 of them are fully funded by the cluster, and 60 of them are coming from different grants, but they choose to be associated with the cluster because they do something similar, and then they can apply for travel funds or they can apply for visitor funds. So they're part of the cluster community, but they are not paid, the salary is not paid by the cluster, but they're supported for computers, for all they need, basically.
Thank you.
No problem.
So, traveling to Paris this weekend and this morning seems to have been a bit disrupted. So, but now Inge Loes has arrived. Okay, hi Inge. So, welcome. And she will talk to us about the Origins initiative in the Netherlands, which is a national initiative, a little bit like ours, and was very inspirational for me because it started 2 years ago. I was invited to their kickoff meeting in designing this one. So, Inge, thank you very much.
Good morning. Sorry I'm this late, but at least I was in time for my talk, but we were stuck by a broken train. So our Origins Center in the Netherlands is a little bit different than most of the things you will probably hear about the rest of the day. So I'm just going to, oh, this is the wrong title slide. I'm going to talk to you a little bit about what the Origins Center is and especially how we came about. Because the Origins Center in the Netherlands is a virtual center, so it's just a lot of collaboration between Dutch scientists interested in questions related to origin of life, evolution of life, potential for life, extraterrestrial life. And so the original aim of the center is to foster collaborations between scientists that generally don't work together, so we organize meetings. And together, well, like we all do here in this audience, we try to address challenges that you cannot do within your own field. First a little introduction about who we are. So we're currently a steering committee of 6 people. This is the second steering committee since we started in 2017. So Sieber and Otto, he's a chemist. Then we have Floris van der Tak, who's an astronomer. Liede Wijlaan, she is a physicist and biophysicist. Bob Planquet, he's a computer scientist, but he does a lot of, a mathematician, but he's more in the biological, mathematical corner of science, Brechtje Wertheim, and she's an ecologist. My name is Inge Loes, and I'm a planetary scientist, astrobiologist. So what we try to do with this steering group is really cover all the fields, or the majority of the fields that are involved, because there's, of course, more fields even, so that we at least have one representative from each field building up our network. So now about our own origins, because we started from a science initiative in the Netherlands. It was called the National Science Agenda, the National Research Agenda. And the idea behind it was actually the government who had realized that there was a huge gap between the general public and scientists. And they also decided that scientists should also be a bit more reactive on the questions that the general public would ask. Of course, this is always a little bit, how are you going to be reactive if you also want to have long-term ideas researched, and if you want to do more like fundamental or blue sky science. But anyway, what they did is they put up this website, and the only thing the website had was one window in which you could type your question to the scientists. And then in total, they accumulated about 13,000 different questions. And there were all kinds of questions, so there were children putting in questions. What we also saw was that lobby groups of patient organizations, for example, put in questions. So there was kind of a disbalance between questions. So then a group of scientists was assigned to the task of bundling these questions into 140 different top-level questions. And then from these 140 top-level questions, this panel synthesized 25 different research routes. And one of these research routes was called the origin, and then we sneaked in evolution, but the origin and evolution of life on Earth and in the universe. So again, the idea was to really bridge this gap between society and science. So the whole idea behind all the different research routes is also that when you apply for money, you can't only be a group of scientists for making up a consortium, but the consortium actually has to exist from, well, scientists from universities, but also from different other types of schooling, at least ranging from middle or applied universities, the more scientific universities, but also societally relevant partners, and even if you could find them, industry partners. So it really, the consortia really have to be this conglomerate of all the different parties that are engaged in this topic. One of the most important points why the government decided to do this was to better foster the trust of the general public in science. Of course, this all happened before COVID, and then there was COVID, so then now we have to rebuild some of this trust again. So this was really, this was the starting point. And then we got together in 2017, and what we did in 2017 is we met up with all different researchers from all the different fields that are interested in these topics. And we sat together and we started building a research agenda. And as you can see, I hope it's a little bit readable, but we have identified several themes in our research agenda that we're trying to address. And well, there is some kind of a line in there, but of course we cannot, for many of these emergence steps, we cannot say whether this is really a chronological order or not, but we start relatively close to home. So we start at the formation of planetary systems. So we start about, 5 billion years ago, more or less. So there's another consortium that's actually focusing on everything before that. And everything also outside the realm of only a planetary system. So we're then focusing on the formation and early evolution of Earth-like planets and moons, emergence of conditions allowing for the origin of life, emergence of the synthesis of molecules that are relevant for life, emergence of life-like functions in prebiotic systems. Then we look at the emergence of Darwinian evolution. And as I said, there is no chronological order in this, so we don't know, we just had to put it in some order. Then emergence of life, interaction between local and planetary scale environments and life. And then we really go towards the more biological questions, so the emergence of genotype-phenotype separation, emergence of contemporary biochemistry, the emergence of a contemporary like prokaryotic cell, and then the emergence of eukaryotes and the emergence of multicellularity. So as you can see, we're really very broad. But what do we actually do? So we started off with this consortium, and then, well, the Dutch government was a little, well, they were doing a lot of throwing a lot of initial ideas around on how these consortia were actually going to get funded. So when we all started, we thought, well, each of the routes gets 10 million euros, and we all, you know, there was money to do that. And then we can all build up our route and do all our research. And then, of course, when we were all happy throwing around ideas, that idea was slashed again. And then they decided that several of the routes were already very well developed, but about 8 were not so much. So these were really new fields that were brought together on a certain topic, and that actually counted for our research network as well. Within the Netherlands, there's a lot of people working on all these different topics, but there is not really, or there was not really a lot of cross-collaboration and interaction between the different fields. So they decided that we were going to be one of the routes who was going to get awarded. Well, we did have to write a proposal, but that could compete for this start impulse. It was 2.5 million euros. So as you can see, it's a little bit smaller than the 45 million euros I just heard. So what we did within this start impulse, and I'm going to show you some snapshot results. So we decided to make sure that we have enough people connecting as well. So we opened 8 fellowship projects. So people could apply and come up with their own research project within the scope of that fellowship project. But we also have money set aside for smaller projects, pilot projects, so that people who would normally not collaborate with each other could apply for a little money to start up a pilot project from which they could apply for bigger funding afterwards. We also organized a conference, and we also had quite some plans on doing different public outreach events to already start bridging this gap between science and society. Some of these outreach projects were, of course, a little bit hampered by COVID coming around for, well, the majority of our program. So we couldn't do much of that, but we still managed to get quite some good results. So one of the things we did is we wrote this research agenda that I already showed you. I couldn't bring copies of that, unfortunately, but if you're interested, please let me know, because I'm happy to send you one of these research agendas and that you have an idea on what we're focusing on in the Netherlands. So we're having newsletters for the community. We also have newsletters in Dutch for the general public to keep them a little up to date on what's going on in the network. We set up a PhD postdoc network where students can meet each other. And, well, we organize several conferences now. So we also did a lot of community informing at the scale that was possible within the COVID timeframe. So one of the things we did was we sponsored episodes of a children's, what is it? It's kind of an informative show, which is partly science, partly news. So they address certain amount of the topics, about 5 topics that we cover within the Origins Center, and translated it to children of about 8 to 12. So we work together with NEMO, which is one of the national science museums in the Netherlands, and they have this big database of a website actually of articles that also students and general public can research. So we worked with them a lot on the different topics that we covered. We started a very successful podcast series last year, so that was also a good way to interact with the public when interaction wasn't that regular at the moment. So this is what we do right now to bridge this gap between us and the general public. So we also have within our bigger scheme of things, we have also a range of smaller networks where people can interact on different topics. So we have a network, a knowledge network on the emergence of homochirality. We have a network on finding extraterrestrial life. We have a network that focuses on bridging long temporal and spatial scales. And this is something that we already put in there very early on, because if you remember the topics that I mentioned, we're really working from very large scale, planet formation, for example, to really small scale. And how can you bridge these scales? How can you bridge, for example, computer modeling skills on the atomic scale to experiments, to large scale projects that are ongoing in nature? And since that also, that's not only a modeling and experimental effort, but it also requires a whole philosophical approach and also an approach on common language, because people from different fields will talk about different topics in different ways. So that's why we have this, this working group that thinks about especially bridging these scales. We have a working group that works on building and repairing life from molecule to ecosystem. We are in this team. We're affiliated with a research network that was already funded before we started, which is called Building a Synthetic Cell. So they're really looking at how can you build a minimalistic cell. So we're collaborating with them on this as well. Then we have a network on the origin and co-evolution of Earth-like planets and life, and a network on predicting evolution of life. So these were the fellows that we employed during the time frame of our Start Impulse. We have a few more than 8, because some of them actually got a permanent position. Because in our case, of course, we train people, and in this case we train postdocs. And yeah, well, there's not so many jobs in the Netherlands at the moment, but of course with this effort we're also hoping that jobs are going to be stirred a little bit more in this direction as well. But at least some of these people got permanent jobs, so they were replaced by new people. So I'm going to show you a little bit the highlights of some of the projects that what we worked on. So one of the things we worked on, and this was Eloy Kamprubi, who was the fellow who was working on this, was building this origin simulator. And one of the things we were trying to do in there, it's of course a huge glove box and a tiny little microchip. And in this microchip, what we're doing is bringing 2 fluids together, and then we precipitate membranes at the boundary where these fluids interact. And then we use these membranes as kind of proton pumps. We have hydrogen-enriched fluids going on one side, and we're looking for the type of mineralogical membrane that actually helps transport the excess hydrogens or the excess protons on one side to the other side, and catalyze reactions to form precursors for organic compounds. So I don't, unfortunately, have any cool end results yet, because we were very put behind because of all the COVID delays. So we're still working on this, but at least everything is up and running. So in a second project, we had a project that worked on predicting evolution. So can we predict evolution? Well, what are the different factors that are involved in predicting evolution? So this was one of the outcomes, a review paper on what are the different goals for predicting evolution and why would you want to predict evolution. Because of course predicting evolution is interesting if you look at the more hypothetical side on what would we think that life outside the Earth would look like. But it's also very relevant, for example, for medication and for how cells can adapt to changing environments ecologically. So this is one of the papers here. You also see it's highlighting vaccines, for example, and how can you predict how diseases evolve as a result of vaccine and antibiotic resistance, for example. So that's what we're trying to do. This is a very nice example on how we address fundamental questions that we also try to give an application, because that is also what the government wants us to do with the funding that we have. So this is another nice example. What they did here is they studied, the group that worked on this studied nematodes, and they put different types of stresses on these nematodes, and you saw that with no stress most of the nematodes were happy and surviving. With more bottlenecks you saw less nematodes actually persisting. But then if they took all the different nematodes out of their condition and put them in sterile waters, actually all these nematodes managed to sustain and started evolving again, which hinted that the nematodes actually have all their important bacteria and their important fungi and the other organisms that they thrive on. That is part of the inheritance to the next nematode. So apparently you can completely sterilize their environment and the nematodes will happily thrive along. So another project was focused on how to better understand big steps in evolution. And what they studied here was looking at how you can fuse cells, but then they specifically focused on cells without cell walls and how that would further the fusion between different types of cells. And here again, the focus was really on the fundamental processes that drive this cell fusion. But again, it had a spin-off, and in this case, it was really focused also on antibiotic resistance again. We had a project on modeling Earth as an exoplanet, and this is one of the outcomes of that project, where the fellow Dennis Heuning, he looked at the effect of life on the evolution of climate and the evolution of the planet, and especially on the climate and climate stability. And what he showed was that if you have weathering with life, your climate is stabilized for much longer than if you have a planet without life, and the climate can be stabilized on time scales longer than 500,000 years. And the last project that I would like to highlight is by Sandro Colisi and Renske Vromans, and they looked at why cells started working together. And they used, I showed here a screenshot of the computer model, so this was really a computational effort. And what they showed was if you have groups of cells, they generally engage better with, if there's a resource somewhere, then they move better towards the resource than when they're by themselves. So there is a evolutionary benefit for these single cells to actually group. But if you start changing the environment too rapidly, these cells that are grouped together cannot give their information to their colleague cells in their group fast enough. So then they're better off with single cells. So these were a few of the things that we managed to do in these 5 years of funding with these 3-year fellowships. So this is basically what we did in these 5 years. And then, of course, after 5 years, the funding ran out. Then we go back to the way that the Dutch funding scheme was organized, because there was actually more money allocated, especially for these routes, to write proposals and grant proposals. But the idea behind the grant proposals is, as I already explained, you couldn't be a consortium of only scientists, so you had to have involvement of society-relevant groups and potentially industry. But in the first 4 years of this funding mechanism, there was the obligation of having a 10% co-financing rule from an external party. So that meant that some routes could easily, or could more easily, get money from these funds because they already had their interaction with parties that could potentially co-finance some of these works. And for our route, it was very difficult because what we had to do, especially to get this 10% co-financing, we always had to spin our fundamental questions that we wanted to address to something more applicable in order to get, for example, small businesses or industry interested. So what we mainly spent our time on in those 4 years while this small batch of money was running, and we tried to keep the community together, was also push the politics to step out of some of these constraints so that it would be easier for the fundamental routes to still have this crossover with the society, but especially get rid of this 10% co-financing, because it was in the case of some of these routes extremely difficult. So I can end this presentation with some good news, because that worked. And we're starting now this year with a new round of funding, and this whole round now has been completely reshaped. Instead of consortia randomly forming and focusing on one small step, the Dutch funding agency has now decided that each route will be allocated twice a fund of, well, still on a small scale compared to some, but of 6.5 million euros. So there will be 2 tranches of 6.5 million euros that are allocated to research related to the Origin Center. And what we did now is just basically split up our themes into 2. So one theme is really focused on origin, and the other theme is focused on evolution. The call for proposals in this round just opened, and the deadline is in March. So we're now putting a consortium together. And the whole idea is again something that hasn't been tried before, so they're trying something new with us, is that everybody who's interested has to write a letter of intent, and you have to be present at a workshop with everybody else who wants to form this consortium. And in this workshop, we just have to make it work and come together and form a consortium, and then with that consortium write a proposal. So that's going to be a very interesting steps forward, of course, because we have the scientists, but we also have other parties that want to be involved, and we all have to make sure that they fit. So these are the themes that we're going to address this time, and the idea is also really that it's going to be a consortium that's going to address with 1 or 2 PhDs or postdocs each of these questions. And the other idea, because we're of course expected to make progress in science, but also to further stabilize the network so that people start working together and can then apply for bigger grants again, and different grants, not from this route. So each of the students also need to have supervisions from 2 different directions to make sure that these people also start collaborating. So what the themes that we've identified now are what sort of physical and chemical conditions are needed to cause life to emerge on a planet, how and when did these life-enabling conditions arise on Earth, how Earth-like planets must be for life to originate that is similar to life on Earth, which molecules were present when life originated, and where and how were these molecules formed, and how and when did molecular, chemical, or cellular functions that life uses arise, and which of these functions already existed before there was life, and how and when did Darwinian evolution emerge. So you can see we're very optimistic for the 6.7 million euros, and I hope we're going to make a few strides. And then in 2 years, in the next call, we're going to focus on evolution on Earth and beyond Earth in the universe. So this is basically what the Dutch Origins Center is currently at. So I think funding-wise, we're probably the smallest party here. But what is really good to see is even though we had only a small sum of money when we started, that we really managed to build a network and that people even now, well, they start knowing each other and they start collaborating and you see all kinds of new projects popping up left and right that didn't really exist because the communities were somewhat separated before we started this whole effort. So in that sense, I think we're in a good way. And well, hopefully in 2024, a consortium will be funded working on this. So maybe in 5 years we can stand here again and give you some nice results. So just to see where we're at, you can find us at origins-center.nl, and if you're interested, I can send you a research agenda so to see how all the different networks in the Netherlands connect. Thank you very much.
So we have time for questions. Didier, I bring you the mic. Good luck.
Well, we're still there. So
I'm doing astronomy, so I'm very familiar with the NOVA Dutch structure, very successful combination of all the astronomy department. So how are you related to the NOVA structure? And your center is very much kind of a flat distributed over the whole country, which what I understand. So how likely is it you can move to something like NOVA, which is very centered to a specific location? So what is the level of discussion you're having? I'm pretty sure you're having, because part of your activity are very, very related to the NOVA activities as well.
yeah, so we, of course, many NOVA people are also involved in our network. The situation regarding NOVA has changed because that was earmarked funding in tranches of 5 years for several years. That construction doesn't exist anymore, so now there is a kind of a follow-up situation, but so how NOVA will proceed is also a little bit up in the air. They just wrote kind of a follow-up grant to continue some of what NOVA is doing. But the standard earmarked funding that there was for the past 25 years, our government had decided that things had to go different. So something like NOVA, I think, yeah, there are other institutions in the Netherlands that eventually it would be great if we can evolve to that. And I think that's also something definitely a long-term strategy. And while we're trying to build the same kind of framework as NOVA has. And also really collaborate with, of course, we cannot do this without the NOVA astronomers. But the whole situation in there is a little fluid, I think, is the best way to say that.
More questions? Questions somewhere? Okay. No, yes. Okay.
No other questions?
Yes, it's coming.
Yes. You've made a very important point exactly at the beginning of your talk, and this point was left out at the end of your talk. The importance of understanding the origin of life, I mean the molecular origin of life, is very probably linked to the emergence of Darwinian evolution and of natural selection in the prebiotic world before life. Because when you talk to a biologist, as soon as you reach this prebiotic stuff, he says, no, there is no life there, so there is no Darwinian evolution there. But actually, probably in the prebiotic world where you have molecules, you have probably some kind of organization which selects important molecules and which drives these molecules up when others are just dying. And this is exactly where we should focus on the laboratory work for that.
Well, that's exactly why we put this in here, because we go here towards origins. So this is all prebiotic, and well, if we manage to make something, then that would be great. But this is really focusing on the prebiotic chemistry towards the origin of emergence of life, and Darwinian evolution is really part of that. So whether you call it Darwinian evolution or not, this is really part in the lead up towards...
Yeah, but on the other hand, you should not also forget that you are going to have zillions of contingencies to all this process, you know, and so this is probably an enormous challenge to find what is the right place, actually, where things have been able to proceed. So this is very well known since Monod in '67, where Monod decided that there would no be life anywhere, you know. So that's interesting. In particular, it's very difficult to imagine how a ribosome is coming to life, in a sense.
Yeah, so that's exactly true. So, but it also depends on the consortium that ends up writing this, wanting to write this proposal, how we're going to build this in, because of course we have to rely on the expertise. But there are some people in the Netherlands definitely focusing on that, so I'm sure there will be a place in the consortium thinking of that.
More questions? If not, I have one. So, to understand how it works, so you come together with a consortium that will reply to the call, and are you planning to allocate all the money to this consortium own proposal, or will you leave some pocket of money for emerging ideas, like we heard before from Barbara, the SEED program, or our own program of scientific
what we try to do,
follow-up?
of course, is we have, what we did with the start impulse that we got, we will design several PhD postdoc projects, but we will always allocate some money, like we did before, for small projects and pilot projects. So people, because if we now just cordon off everything, then we need to have some playroom. Sounds a bit silly, but that I think we should have that. So that's definitely what we did last time. It depends, of course, a little bit on the constraints that we will be put under, but I'm sure we will find a way to allocate some money to, well, small grants for people to just follow some new ideas that pop up during the program.
Okay, very good. So this ends the morning. There should be a lunch, a buffet offered by PEPR in the foyer out there. So we reconvene at 2, so almost 2 hours, which is good, so that people can talk to each other. And this is one of the goals, establishing networking within the community. The executive committees and our foreign guests, we will segregate today because we meet in another room in order to try to formalize these collaborations better and see how we can do that. So today we're not mixing with the rest. I'm sorry, but from tomorrow we'll be all together, of course. So we reconvene at 2, and Didier Queloz, not Daniel Queloz, unlike what's written on the website, sorry, will speak about his projects in Zurich and Cambridge, and then we continue from there. Thank you.